Hi, this is Lizzie presenting my final project for CS50. I used to live at Cabot when I was studying in my actually graduate studies for biology. I had zero experience in computer science. That's why I'm taking the CS50. And I'm trying to apply the conserved domain database retrieval tool in my own code space. So as you already know, AlphaFold was trying to predict whether it's AlphaFold 1, 2, or 3. The most recent one is trying to predict the protein structure, which can be verified by cryo-EM in biology. So the next thing that is important after the protein structure, it is how each domains of each protein works. So that's my biology thesis actually back then. And I did it manually. So now I'm trying to create a system that can automatically run the conserved domain database through the database that you can retrieve what is the domain architecture for each gene. So in this CS50 final project, basically I created a small web app, the Flask web app, that lets a user, whether it's a biologist or anybody who's interested in a particular gene, to type in the gene name. So anybody can type in their gene of interest, and the back end, it retrieves the corresponding human protein sequence from the NCBI database, which is called NRAD protein database, and then compute and display the protein's conserved domain architecture. Let me elaborate a bit more about the conserved domain architecture. Basically, each gene of our 22,000 genes of human protein evolves from somewhere. And each gene has particular domains, let's say how the structure looks like. There's a key skeleton of this domain. And the domain architecture is how each domain is structured in this, let's say it's like a building, you have the skeleton. And this domain architecture defines how this gene functions. And conserve is just how it is conserved over the evolution, because honestly, we don't create a new gene, it's just conserved from all the evolution that we have been through. And the NCBI has already annotated the conserved domain name. So it's called CD search. And it is the same RPS BLAST against the CDD, which is a conserved domain database pipeline that powers the original CDart tool. So basically, we're trying to call the NCBI, okay, so this is one gene. And as a biologist, people just type in the sequence. But for ordinary users who are not a biologist, you could just type in a name. Let's say a cancer, it's a very, relevant gene in cancer biology is called c-MYC. So you could just type in MYC, MYC, and then the system will go through the NCBI database to say, okay, actually I used UniProt. To go through UniProt to see what is the sequence of this gene and use that gene to search the NCBI CDD already annotated database and to retrieve what is the domain architecture. So let me give you a presentation of how this thing works. So let me refresh. So let's say one of the gene that is of interest to me is called CYT1, which is one gene that is very important. Okay, maybe I'll give you a quick introduction of the website. So it's called CDart Explorer, and this is where you type in the gene name, or it could be a code. And one of the genes that I am interested in is called synaptotagmin. So, somebody spent 40 years studying this gene and are still studying this particular gene. So this is a very important gene in the neural network of the brain, as in how each neuron connect through the synapses. And there are thousands of genes that is important for synapses, and maybe over 100 genes that is very well studied. So this is one of the most well-studied gene. Is called synaptotagmin, in short, CYT1. So you type in CYT1, and then it will search automatically of how this gene, what is the sequence of this gene. 1 second. What is the sequence of this gene? Oh God, error, problem. Okay, let's refresh. Okay, what is the sequence of this gene? And through this gene, which is probably, yes, 800 amino acids. It's still a pretty big gene. And you use this sequence to go through the CDart database that NCBI has already created. And then this is the domain architecture. So it starts with the lectin domain, and then continue by the olfacto domain. And then this is unknown, unnamed, but it's quite prominent. And then you have the gain domain and the GPS domain. So this is the domain architecture of this particular gene. And this project is interesting. And this project is interesting because it's like the artificial intelligence. Why the artificial neural network is important, is interesting, is the one paper called "Attention is All You Need." So you go through all the database of the large language model, which is all the language based, and you go through all the data with attention needed for particular node, or they put into different nodes to create the connection. That's my understanding. And in terms of biology, we have thousands of millions of genes and billions of the sequences for human genome project. But at this moment, yes, the structure we already figured out with AlphaFold. But how each gene talk to each gene, which means the protein-protein interaction, is at the core of biology. And this domain architecture is the attention is all you need phase for the biology world. So that's why I'm very interested in implementing this project. I'm still working on this, and this is just very first step and initial version of what can be completed in a very short time span. So I hope you enjoy my presentation, and you'll see this is an adhesion GPCR, which is very interesting.